So we can write total electric field intensity at point P, E is equal to E plus Q cos theta minus P cap, because P cap is negative to positive, it is going positive to negative, plus E minus Q cos theta minus P cap. So E plus Q and E minus Q are equal, so we can write minus 2, or we can write 2 E plus Q cos theta minus P cap. Now we can put the value of E plus Q and cos theta from this triangle here. So the cos theta will be equal to here A upon this under root. So we can write cos theta is equal to A upon under root of R square plus A square. And E plus Q already we know its value. So we can write here E is equal to twice of here Q upon 4 pi epsilon naught R square plus A square into A upon under root of R square plus A square, that is minus P cap. Now we can write Q into 2A upon 4 pi epsilon naught R square plus A square raised to power 3 by 2 minus P cap. This can be written P upon 4 pi epsilon naught R square plus A square raised to power 3 by 2 minus P cap. If we are taking R is much more greater than A can be ignored. So we can get P upon 4 pi epsilon naught R cube minus P cap. So here net electric field intensity is this, but the direction of net electric field intensity is opposite to the direction of the dipole moment. And see here, in the electric field intensity at equatorial line and at a point on the axial line, they are different. At a point on the axial line is twice of the electric field intensity at a point on the equatorial line. So this is about the electric dipole and electric field of the electric dipole. Now see here electric dipole in uniform electric field. Suppose this is the direction of uniform electric field I have taken. And in this case, when the uniform electric field is here, when we draw it, we take care of the separation that should be equal between these lines. So electric field lines for uniform field can be drawn like this. Suppose an electric dipole is like this here. This is your plus Q and this is your minus Q. Separation is 2A and this angle is suppose theta. Now the force acting to this side is QE and this side is your minus QE. So net force on the dipole, net force is equal to QE minus QE is equal to 0. So when electric dipole placed in uniform electric field, the net force experienced by this dipole is 0. It means there is no translatory motion. So when the dipole is placed in this uniform electric field, no translatory motion of the dipole. But see here, these two forces are acting along the two different lines. Like this force is acting along this line, this is acting along this line. So when these two forces are acting along the two different lines, having the different line of action, they must produce here torque. So we can calculate the torque acting on the dipole. So in this case, we have to take here the perpendicular distance between these two forces. Suppose this is the line of action for this is the line of action for this. So perpendicular distance is this, that can be written 2A sin theta, because this is also here the theta. So the perpendicular distance between these two forces is 2A sin theta. So the torque can be written magnitude of the either force into perpendicular distance. So the magnitude of either force is QE and into perpendicular distance is 2A sin theta. So we can also write torque tau is equal to PE sin theta. So or we can write torque is equal to vector P cross vector E. So the torque is the cross product of the electric dipole moment and electric field intensity. It means the direction of the torque is perpendicular to the both electric dipole moment and electric field intensity here.